Well, before we talk about inverse functions, which is our topic of the day, we should first know what inverse means in general. So this is going to require a bit of a detour. So we're going to define something that you've actually used many times throughout your mathematical careers, but you've probably not heard this particular term. So this definition is a group. This is a set G paired with an operation, which we're going to call star here, which takes two elements in G, A and B, and assigns them to a new element, A star B. A group must satisfy four properties. 1, there must be an identity element, I, in G, such that when you operate I with any other element, so I star A, you always get A, or A star I still gives you A, regardless of what order you operate them in, for all elements A and G. There must also be inverse elements, so for each A and G, there is an inverse, which we write as A with a -1 in the superscript position in G, such that A star A inverse equals I, and A inverse star A equals I. So in other words, when you operate a number with its inverse, you get the identity back. They must also satisfy associativity, meaning if we're operating A, B, and C, and we operate A and B first, or we operate B and C first, it's not going to change the result of the operation. And finally, closure. If A and B are both in G, then A star B is in G. So, okay, this sounds like a complicated definition and something totally new, and what is this? But actually, you've been dealing with a lot of groups, and it's pretty straightforward. So let's just take a look at addition. So here's basic things you know about addition. You know that 0 plus a number, in this case 3, 0 plus 3 is 3, and 3 plus 0 is 3. And that's because 0 is the identity for addition. So addition with the set of integers has an identity element. So the operation here being plus. So what else? Well, we should have inverses. Well, when we take 4 and we add -4, we get the identity, which is 0. Or if we take -4 and add 4, we get the identity, which is 0. So that means negatives are the inverses for addition. So addition satisfies our first two properties for a group, that it has an identity element, and that it has inverses, which we call negatives. And it's associative, meaning 2 plus 3, then adding 4 is the same thing as if I added 3 plus 4 first, and then added 2 plus that result. And finally, if we're looking at the set of integers, 6 plus 2 is an integer. Any 2, the sum of any two integers, gives you a number that's still an integer. So, and that satisfies closure. So addition on the set of integers forms a group. All right, multiplication also forms a group. In particular, multiplication forms a group with the set of rational numbers, that's fractions whose numerator and denominator are integers, excluding the number 0 forms a group. So we'll look at why we have to exclude 0 momentarily. So first of all, what about an identity? Well, multiplication has an identity, that's the number 1. If I take a fraction times 1, I get the same number. If I take 1 times that fraction, I get the same number. Reciprocals are the inverses for multiplication. So 5 times 1/5 equals 1, the identity for multiplication. And 1/5 times 5 equals 1, that's the identity for multiplication. Okay, so far we've got an identity, we've got reciprocals. What else? Well, multiplication is associative, meaning if I operate, let's say 1/3 times 2/4 times 3/5, if I multiply these fractions first, I'll get the same thing as if I multiplied the 2/4 and the 3/5 together first, and then multiplied it by 1/3. And finally, the product of two rational numbers is also a rational number, right? If I take two fractions, multiply them together, still get something that's a fraction, that's still a rational number. So multiplication with a set of rational numbers, excluding 0, forms a group. Okay, why do we have to exclude 0? Well, because 0 times anything is 0, which means there is no inverse for the number 0, because you can't get 1 by multiplying something by 0, right? So 0 has no inverse, and hence we have to exclude it when we're talking about forming a group on multiplication. Okay, so notice that using inverses is actually how we solve basic algebraic equations, right? This is the key thing to understand. The value of this relationship of understanding the relationship of inverses within these various types of groups is that inverses are how we actually solve equations. So if we look at this first equation, 5 plus x equals 7, what I can do here is just add the inverse of the component paired with my x to each side of the equation. And what do I get? I get -5 plus 5 is 0, the identity for addition, which leaves me with just x equals 7 minus 5, which is 2. So how did we solve this basic equation? We applied an inverse, and since the operation we were trying to undo here was addition, we applied the inverse under addition, which is just a negative number. I know that seems like I'm maybe making it seem complicated here, but actually what I'm trying to do is relate inverse functions, which we're going to talk about momentarily, to 2 different types of inverses you already know, because I want you to understand what makes a function inverse an inverse. It's not the same thing as negatives or reciprocals. It's a different type of inverse, but it's still an inverse, and it gives us the same type of benefits that these inverses give. So let's look at this example here. 2/3 times x equals 4. So here, I look at my multiplicative inverse because what am I doing? I'm multiplying 2/3 times x. I want to solve for x or isolate x. So I multiply by 3/2. That's the reciprocal or the multiplicative inverse of 2/3. So I do the same thing to both sides. And what do I get? Well, these multiply together. They give me 1 times x, which is just x. So this is 4 times 3/2. That's 12/2, which is 6. So, using additive inverses and multiplicative inverses allows us to solve basic algebraic equations. So now we want to consider what does it mean for a function to have an inverse. It's not the same type of inverse, so this is the thing to keep in mind. The type of inverse you're dealing with is dependent on the operation that you're working with, as well as the set that you're using that operation on. When we talk about functions, we're not going to use addition or multiplication to define an inverse. Instead, we're going to use composition. So, when discussing inverse functions, the operation we use is the composition of functions, f of g of x. So in order to identify the appropriate inverses under composition, we have to know what an appropriate identity function is. Well, we've mentioned this identity function in the past, but this gives us the second reason we call this the identity function, which is because when we compose I of x equals x, we get the same thing, right? So the identity function, as we've seen before, is the function that's just y equals x, or in this case, we've written it as I of x equals x. Again, that should make sense. What should an identity do? An identity, when you compose them, should give you the same function back that you started with. So when I operate f with I of x, I should just get f of x, but that means, of course, I of x equals x. Okay, hopefully that's clear. So, just like multiplying reciprocals gives you 1, or adding negatives gives you 0, composing the inverse functions should give you the identity x. So the inverse of f, written f superscript -1, now is the function that satisfies f of f inverse of x equals x, and f inverse of f of x equals x. So I want to be really clear. F inverse is not 1 over f. Do not do that. These are not equal. This is the most common mistake I see dealing with inverse functions, and this is absolutely not correct. So the reason we use the same notation here is because they both mean inverses. when we're talking about numbers, right? When we're talking about numbers, the negative first power, say 3 to the negative first power, means 1/3. Because we're talking about numbers under the multiplication operation. But when we're talking about functions, this notation means the inverse under composition, not multiplication, right? So what it means to be the inverse is that this is true, that when you compose a function with the inverse in either order, you just get the identity back, and the identity for composition is x. That's the key thing here. Do not try to do this. You have to just understand that what an inverse function means is that you compose them and you just get your input back. That's all. Okay, so hopefully that makes sense and clears up this really common confusion. And that's a big part of why I wanted to go into detail into this distinction, is because this is one of the most common pieces of confusion that I see. And I don't want anybody to make that mistake. These two things aren't equal. F inverse is not 1 over f. Instead, F inverse means that when you compose them, you get your input back. All right. Hopefully, I've been really clear about that. I feel like I harped on that quite a bit, but I really want to make sure that nobody makes that mistake because, if I can avoid it, I don't want people to make unnecessary mistakes. So here, we're being asked to confirm that f of x equals 2x plus 7, and f inverse of x equals x minus 7 over 2 are inverse functions. So if we want to confirm this, what we need to check is this. Check that they satisfy what it means to be an inverse function. So f of f inverse of x means f evaluated at x minus 7 over 2. So just like with composition of functions before, this means for the function f, we're going to replace its input x with this whole expression. So this gives me 2 times x minus 7 over 2 plus 7. The 2 over 2 cancels, and we get left with x minus 7 plus 7, and negative 7 plus 7 cancels, and we're just left with x. So far, so good. But remember, we have to check that it works in both orders, not just when you compose f inverse inside of f, also the other way around. So f inverse of f of x gives us what? So that's f inverse evaluated at 2x plus 7. So here, we're taking the x in my f inverse function and replacing it with the whole expression 2x plus 7. So this is 2x plus 7 minus 7 over 2. And there's nothing multiplying by the parentheses here, so we can drop that and just say 7 minus 7 is 0. So this is 2x over 2, which is just x. So that's good. So yes, these are inverse functions. Okay, so hopefully the picture here is becoming a little bit more clear about what an inverse function is. So now we should ask ourselves a big question. Do all functions have inverses? So, well, let's have a little hint here. If we go back to multiplication, we could ask ourselves a similar question. Do all rational numbers have inverses? And the answer is no, because 0 has no inverse. So the answer here is also no. Not all functions have inverses. So we have to figure out, okay, why? So what restrictions are required to guarantee that a function has an inverse? So let's think about what's happening, what else we can determine based on this definition of an inverse function that we're using here. Okay, so what else can we determine? Well, we know that f inverse of f of x should always be equal to x. So that means that f inverse of f of 1 should be equal to 1, right? So what does that tell me? Well, f inverse of f of 1 should be 1, but f of a 1 is a, so this is the same thing as saying f inverse of a equals 1. So let's go ahead and make a little table for f inverse and see what this table looks like. Okay, so here, the input a for f inverse gives me the output 1. All right, so let's do the next one. F inverse of f of 2. Well, the definition of an inverse tells me that this should just be 2. F inverse of f of x is x. Okay, but f of 2 is b, so this is the same thing as saying f inverse of b. So when my input is b for f inverse, my output should be 2. All right, let's take a look at our last one, f inverse of f of 3. Okay, well that's f inverse of c, but this should be equal to 3, right? So f inverse of c is 3, so when my input is c, my output is 3. Okay, so let's think about what do we see here between our inputs and outputs? Okay, so if a function has an inverse, the inputs and outputs switch. That's a key thing to understand here, right? Is that by this definition that the composition of inverse functions is x, we get the immediate result that if we have an inverse function, it must switch inputs and outputs with the original function. That has to be true. So let's take a look. We've seen that functions and their inverses must switch inputs and outputs. So what could cause a problem here? So let's look at this function on the left here. Just pay attention to this for a moment. Here, this is a function. We've got x is 1, 2, and 3. And when x is 1, y is a. When x is 2, y is a. And when x is 3, y is c. This is fine. We don't have anything that makes this not a function. Each input only has one output. But notice that the two inputs, 1 and 2, go to the same output. So if f had an inverse, it doesn't, but if it did, this inverse, we would expect it to look like A1, A2, C3. So this is a problem, because here we have the same input A going to two different outputs. So this is not a function. Yeah, so the input A has two different outputs. That makes it not a function. So since f inverse is not a function, well, what restriction do we see that we need here? Well, we see that it's necessary for a function to have only one input that corresponds to each output in order for that function to have an inverse. In other words, each input can't go to the same thing. We can't have two inputs going to the same thing, or there won't be an inverse function. So we have a special name for that property. It's called the one-to-one. And so formally, how do we write this? The definition is a function is one-to-one if for any two elements, x1 and x2, f of x1 equals f of x2, if and only if x1 equals x2. That definition may seem a little bit weird, but it's actually pretty straightforward. What this says is, if your outputs are the same, you must have had the same inputs. You couldn't have had different inputs. So notice, this function is not one-to-one, because here we had the same output, but our inputs weren't the same. So this function would not be one-to-one. All right, just had a little bit of a bizarre issue. Screen kind of cut out. I'm not sure if I lost some stuff there, but it claims I'm still recording. So let me see if I can pick up where I left off. Hopefully, we'll be in good shape here. Okay, so f of x here is not one-to-one. Okay, so in other words, we've got the same output, but actually two different inputs. That definition of one-to-one says if you had the same output, you must have had the same input. So we can think of this property as the horizontal line test. So if we have two inputs, x1 and x2, all right, they can't have the same output, right? Or it's not one-to-one. So if a horizontal line passes through two or more places on the curve, the function is not one-to-one. On the other hand, if any horizontal line only passes through the curve once, then we would say that that is one-to-one. All right, so let's go ahead and move along here. So to summarize this, we say that the operation of composition forms a group on the set of all functions which are one-to-one. In other words, if a function is one-to-one, it must have an inverse. That's the key thing. If a function is one-to-one, we know it has an inverse. Now, important fact, since functions and their inverses trade inputs and outputs, that means they also trade their domain and range. So if a function f has domain A and range B, then f inverse has domain B and range A. All right, so to summarize this, we're going to write two different versions of our definition for inverse functions. And this version 1 is exactly what we've called it before, how we initially defined this. Let f be a one-to-one function, then its inverse, denoted f inverse, is the function that satisfies both f of f inverse of x equals x and f inverse of f of x equals x. Now, definition version 2 is that immediate result we talked about before. Let f be a one-to-one function. The inverse of f, denoted f inverse, is defined by being the function such that f inverse of y equals x if and only if y equals f of x. So what does that mean here? That just means that your inputs and outputs switch places between the inverse function and the regular function, or the original function, I should say. All right, so let's put this to use. We've spent a lot of time trying to make sure that what an inverse function is actually makes sense. So I hope that you've got a pretty clear understanding of the definition of an inverse function now. So let's apply it. So assuming that f is one-to-one and has domain negative infinity to infinity, if f of 2 equals 7, find f inverse of 7. Well, f inverse of 7 must be 2. Definition, version 2. Right? This definition says that inverse functions switch inputs and outputs with the original function. My input here was 2, my output was 7. So now if I look at the inverse function and my input is 7, my output must be 2. That's all there is to it. There's nothing else. So don't overthink these. Just keep in mind, if you understand these two definitions, you understand really everything you need to know about inverse functions to succeed with this material. Okay, now for B here, if f of negative 5 equals 22, find f inverse of 22. Okay, that's negative 5. Again, this is just definition version 2. All right, C, if f inverse of 3 equals 0, find f of 0. Well, f of 0 must be 3. Again, inverses and the original functions switch inputs. And it doesn't matter which order you look at it in, whether you're looking at the original function, then the inverse values, or vice versa, they still switch inputs and outputs. All right, so example 6 here. Assuming that f is one-to-one with domain negative infinity to infinity, evaluate f of f inverse of 3. This is just 3. I don't need to know what f looks like here, because I know that the definition of an inverse function says that when I compose inverse functions, I get my input back. F of f inverse of x is x. In this case, f of f inverse of 3 is 3. That's all there is to it. And it doesn't matter which order I compose them in, the same thing applies. So this is definition version 1. F inverse of f of 25 is 25. That's all there is to it. F of f inverse of negative 5 is negative 5. That's all there is to it. So don't make these problems more complicated than they need to be. They really just boil down to understanding these two definitions. If you understand those definitions, you should be on pretty good footing with this type of problem. Okay, so example 7, show that f of x equal to 2x plus 7 is a one-to-one function. Well, what we want to look at is f of x1 equals f of x2. So show that if this is true, it implies that x1 is equal to x2. So let's see. Well, 2x1 plus 7 equals 2x2 plus 7. Well, if I subtract 7 from both sides of the equation, what does that give me? Gives me 2x1 equals 2x2. And so if I divide both sides of the equation by 2, what does that give me? Gives me x1 equals x2, which is exactly what I want. So yes, this is one-to-one. And that's just the definition of being one-to-one. So that's why, even though that definition for one-to-one may seem a little weird at first, it's important to understand because that definition gives us a precise way to deal with showing that a function is one-to-one. Because we can't always graph a function, right? So it's not always clear. We can't just draw a picture and figure out if it's one-to-one. But if we understand that definition, we can apply it directly and show that a function is one-to-one. All right, so now find the inverse of f of x. Well, what do we know? We know that inverse functions switch inputs and outputs. So what I'm going to do is instead of writing this as y equals 2x plus 7, I'm going to switch my input and output and write x equals 2y plus 7. So if I subtract 7, that gives me x minus 7 equals 2y. And if I divide everything by 2, that gives me y equals x divided by 2 minus 7 halves. I could also write this as x minus 7 all over 2. Now notice, this is exactly the same ones that we already verified were inverses to each other using the definition before. All right, so we've already shown that these are inverses for sure. And here we're seeing, well, we used the other version of the definition to show that they were actually inverses. But if we want to find the inverse, typically how we'll deal with that is switching the inputs and outputs and resolving. And then this new function gives us our inverse. All right, so let's take a look here. Given f of x equals 5x minus 1 cubed, all cubed, plus 2, find f inverse and verify the answer. All right, well, we're going to take the same approach. So this is my y, this is my f of x. I'm going to switch my input and output and write this as x equals 5y in parentheses minus 1 cubed plus 2. And now I'm going to resolve this equation for y. So I'm going to subtract the 2. I get x minus 2 equals 5y minus 1 cubed. Now I want to cancel this cubed, so I'm going to take the cubed root of both sides of the equation. So this becomes the cubed root of x minus 2 equals, now the cubed root cancels the cube, and that gives me 5y minus 1. Now if I add 1 across, that gives me 5y equals the cubed root of x minus 2 plus 1. And now if I divide by 5, that gives me y equals the cubed root of x minus 2 plus 1 all over 5. So this is my inverse function. All right, let's do one more of these types of problems here. Given f of x equals x plus 2 divided by x minus 3, find f inverse and verify the answer. So same approach here. Switch x and y. This is my y value. So this is x equals y plus 2 over y minus 3. Now solving this one for y is a little trickier. Let's multiply the y minus 3 across. So we get y minus 3 times x equals y plus 2. Now I'm going to distribute this x. So I get x times y minus 3x equals y plus 2. Now I'm going to move my y to the left side here and the 3x to this side, so I get xy minus y equals 3x plus 2. And I'm going to factor a y out on the left side of the equation. And now I'm just going to divide by x minus 1. And I get 3x plus 2 over x minus 1. So now we want to check that this f inverse function is correct. So let's verify it by checking the first definition. So this is f of 3x plus 2 over x minus 1. That's 3x plus 2 over x minus 1 plus 2 divided by 3x plus 2 over x minus 1 minus 3. So all I've done here is plugged in this internal function here into my original function. And now we've got a little bit of algebra to do here. So I'm going to find a common denominator for the top and bottom, which is going to be the x minus 1 here. So this is 3x plus 2 over x minus 1 plus 2 times x minus 1 over x minus 1. So I just multiplied 2 by x minus 1 over x minus 1 here. And then I'm going to do the same thing down here. I'm going to multiply 3 by x minus 1 over x minus 1. So now, in my numerator, I get 3x plus 2 plus 2x minus 2 all over x minus 1 divided by 3x plus 2 minus 3x plus 3 over x minus 1. So up here we've got 2 minus 2 cancels, and down here we've got 3x minus 3x cancels. So this gives me 5x divided by x minus 1 over 5 divided by x minus 1. And division of two fractions is the same thing as multiplying by the reciprocal. So we can rewrite this as so, and cancel x minus 1 over x minus 1, and 5 over 5, and we get left with x. So that's good. Now, we still do need to check f inverse of f of x, but it's going to be basically the same algebra, and so I'm going to leave that as an exercise to the viewer. But you'll get the same thing. If you do this composition in the opposite order, you'll get x, and you'll see that yes, you can verify this is the correct inverse function. Okay, so that's example 10. Now we have one more problem to look at here, which is a little bit more involved. So for this type of problem, we really do have to take a little bit of time to think carefully about what we're doing, and try to, problem solve it as best as possible. So the boiling point of water is 373 degrees Kelvin, or 212 degrees Fahrenheit. The freezing point of water is 273 degrees Kelvin, or 32 degrees Fahrenheit. The relationship between Kelvin and Fahrenheit temperatures is linear. Write the linear function expressing k of f in terms of f. So, we've been told explicitly that this is a linear relationship, which means that we should be able to write k as m times f plus b, where f is our independent variable and k is our dependent variable. Now the question is figuring out what m and b are. All right, so for that we've got to do a little bit of algebra. we've been given two sets of inputs and outputs. We should think of this as like x1 and y1. And we should think of this as x2 and y2. So let's plug in those values and see what we get. So for 373 degrees Kelvin, we get m times 212 plus b. And for 273 degrees Kelvin, we get m times 32 degrees plus b. So now we want to solve this system of equations. And so we do it like we would pretty much any other regular system of equations. So I'll start by isolating b here. I get 373 minus 212m equals b. And then I'm going to plug that into my second equation. Gives me 273 equals m times, or I'll rewrite this as 32m, plus, and then I'll substitute this b in. That's 373 minus 212m. So if I subtract 373 from each side of the equation, I get negative 100 equals 32m minus 212m. Okay, so 32 minus 212 is negative 180. So this is negative 180m equals negative 100. So if I divide that out, I get 100 divided by 180 equals m. That's 10 over 18, which is 5/9. So m equals 5/9. Now we just need to find what b is. We could do that by just plugging that into the equation we isolated for b before. So this gives me 373 minus 212 times 5/9 equals b. Now my suspicion is that 212, well let's see, 212 is not divisible by 9 actually. So let's just go ahead and combine this together best we can. So I'm going to rewrite 373 as a fraction over 9. So this gives me 3,357 over 9. I just used a calculator to multiply that by 9. Minus 212 times 5. It's 1,060 divided by 9 equals b. All right, so 3,357 minus 1,060 gives me 2,297 over 9 equals b. Okay, so that's pretty much it for that. All right, so that gives us the relationship k equals 5/9 times f plus 2,297 over 9. Now, in general, this number is approximately 255.2. So you might typically use just 255 because it's close enough for most conversions. But I'm going to go ahead and keep this exact. All right, so we wrote a linear function expressing k of f in terms of f. Find the inverse of the function. What does it mean? All right, so I'm going to reuse or rewrite this in terms of x and y here, because I don't want to cause unnecessary confusion. So usually we denote x to be our independent variable and y to be our dependent variable. But in the case of this, k and f specifically represent Kelvin and Fahrenheit, So they should be fixed, right? They're not based on whether it's an independent variable or not. So let's just start by finding the inverse, and then I'll show you what I mean. So we'll write this in terms of y and x. So I switch to x equals 5/9 y plus 2,297 over 9. I subtract that, I get x minus 2,297 over 9 equals 5/9 y. And then I multiply both sides by 9/5. So that gives me y equals 9/5 times x minus 2,297 over 5. Now, here's the thing. Here, we switched our inputs and outputs, but in terms of which one represents Kelvin and which one represents Fahrenheit, you know, those should have carried along with the switch. So in other words, this should look like Fahrenheit equals 9/5 Kelvin plus 2,297 over 5. So what does this mean? That's the key part here. What this means is that the original function allows me to convert from Fahrenheit into Kelvin. So if I'm starting with a Fahrenheit value, the function lets me convert this into Kelvin. The inverse function says, hey, if you're starting with the Kelvin value, plug it into here, and it'll give you the Fahrenheit value as an output. So hopefully that makes sense. All right, so a normal human body is 98.6 degrees Fahrenheit. What is the corresponding Kelvin temperature? So if I want the Kelvin temperature, I just take my equation, 5/9 times 98.6 degrees plus 2,297 over 9. Don't really need to write degrees here. And then you just plug it into a calculator, so that's kind of plug and chug stuff. 5 times 98.6 divided by 9 plus 2,297 divided by 9. And I got exactly 310 Kelvin. Okay, so that's it for this video on inverse functions. I hope that you have a stronger understanding of what an inverse function is and why it's useful. And you will use this concept constantly throughout this course material. So please make sure you pay special attention to the definitions for inverse functions, because they're going to save you a lot of hassle in understanding future concepts as we move forward. All right, well, thank you very much for watching. Have a great day.